Welcome to Transfer Phenomena in Bioprocess Engineering, Week 6, Lecture 3. Minimum fluidization velocity and bed expansion in fluidized-bed reactors. So, by end of the lectures, we will be able to learn the concept of minimum fluidization velocity, that is we called as the U of MF. Then also describe the hydrodynamic conditions below, at, UMF, and then above that what will happen, that fluidization part. So, then derive the governing equation for minimum fluidization for applying the force balance principle. Then of course, if you incorporate the Ergun equation to determine the critical fluidization velocity. Then analyze the mechanism of bed expansion by relating the superficial velocity, that is a bed porosity is there, epsilon, then bed height, expanded bed height when during the fluidization time. So, finally, evaluate the effect of the particle properties, the fluid properties, that means density, viscosity, then what condition, operating condition, temperature, pressure on fluidization behavior, and apply this principle in design of the fluidized bed bioreactors. So, flow in fluidized bed, introduction of what is minimum fluidization velocity. What is minimum fluidization velocity is the lowest fluid velocity at which the packed bed begins to fluidize. So, when the minimum fluidization velocity, the packed bed got the fluidized one, that point called as the UMF, we call as the minimum fluidization velocity. So, at this critical velocity, what will happen? The upward drag force exerted by the fluid exactly balance of effective weight of the particle, so causing the particle to become suspended. That is meaning that here there is a FD drag force there, FD equal to the drag force, upward drag force, then W effective. So, both are equal when the minimum fluidization velocity happening that time. So, below this velocity, if you go below this velocity, the particle remain fixed, because the minimum fluidization velocity only, that time only the particle get slowly suspend this one. So, the above the velocity, the bed behaves completely fluidized bed. Whenever the below the velocity, it behaves as a remain fixed bed. There is a two way, one is UMF less than UMF, it behaves as a big fixed bed. The above UMF, above minimum fluidization velocity, it behaves as a fluidized bed. That is a flow condition, case 1. If it below minimum fluidization, what will happen? When the superficial fluid velocity is less than the minimum fluidization velocity, the drag force is insufficient to the support the particle, because if it go below, the drag force is a very low, it is insufficient to the support the particles. So, what will happen if minimum fluidization velocity here compared to the superficial velocity, the particle remains stationary, because that we called as a fixed bed. The bed behave as a packed bed, there is a packed bed, or we can write a fixed bed, both are same, packed bed and fixed bed both are same. So, there is no particle movement, or there is no bed expansion. So, what will happen at minimum fluidization? At minimum fluidization, when U equal to UMF, there is a U equal to less than UMF, then what will happen? That one, then if U equal to UMF, what will happen here? So, when the fluid velocity reaches U equal to UMF, that we called as a minimum fluidization velocity. So, that means that the upward drag force equal to the effective particle weight. So, this we always called as a minimum fluidization condition or minimum fluidization velocity. What will happen at this point? So, if it below, what will happen, and then if it equal, what will happen? So, there is a fluidization begins, because that will start the fluidization, the particle are just suspended at one. So, the pressure drop across the bed reaches the particle weight per unit cross sectional area, then this marks exactly the transition from packed bed to fluidized bed. This point at the minimum fluidization velocity, it moves to packed bed to fluidized bed. So, then case 3 what will happen? If above minimum fluidization, that UMF is the very high, what will happen here? So that time when the fluid velocity exceed the minimum fluid velocity, that is the UMF is a very high, then what will happen? Then automatically the drag force, the FD become greater, because the drag force greater than the particle, there is a particle, effective particle weights are there. So the FD is a very high. So what will happen at this point? Then consequently the particle moves freely because of this velocity very high, then automatically its bed starts to expand, that one. So then the distance between the particle also increase, because it gets fluidized, then definitely the particle also increases here. Then the bed porosity, void fraction also get increased. The epsilon, when fluid if fluid bed starts to expand, then automatically the bed porosity also increases here. So finally the system behave completely fluidized bed with the excellent mixing, and then it enhanced heat and mass transfer. So then what are the parameters affecting the minimum fluidization velocity? So there is so many parameters are there, how the parameters getting affected, because we are seeing so many equation. There is a density, then particle diameter, particle density, viscosity, then velocity, all these are parameters. But here what is the parameter affecting the minimum fluidization velocity? There is a U, M, F. For UMF, what are the parameters getting affected here? So the value of UMF is influenced by both particle properties and then of course the fluid properties also, because the UMF minimum fluidization velocity will be affected by, influenced by in particle properties and then fluid properties also. So what is the particle diameter? We call it dP, particle diameter. So it's always in terms of meter. So the larger particle, the particles are very large, it have a greater mass. If larger particle is there, it have a greater mass, then therefore it require large drag force also need to become suspended. When the particle are more, then the drag force also we need more to become suspended. So then consequently the large particle requires higher minimum fluidization velocity, not lower. We need higher minimum fluidization velocity because the particles are large. Then next one is for next parameter, which one is affecting the minimum fluidization velocity. There is a particle density. The first one is the diameter, then the density. Density we called as a kg per meter cube. The diameter we write in terms of unit is meter. So here the heavier particle, it always have greater effective weight, because the weight, the particles are heavier, then it give greater effective weight. So then we need more drag force, same way needed to balance this weight. So then if you higher particle density is there, we need higher UMF, higher minimum fluidization velocity. If particle density also more, if particle diameter also higher, then we need higher minimum fluidization velocity. These are 2 points. So the 2 parameters we discussed. Then next is the fluid density, that is a rho F, we write rho F. There is a denser fluid, it provides a greater buoyancy force on the particle. This really reduce the effective particle weight. So therefore if higher fluid densities are there, then we need lower UMF. There is a fluid density, not particle density. Okay, this is a fluid density. There is a fluid, what we are using, the fluid, gas, liquid, solid, that one. If higher fluid densities are there, then automatically it is a lower of minimum fluidization velocity need. So what will happen for fluid viscosity? If viscosity determines also how efficiently momentum is transferred from the fluid to the particles. So if viscosity high, then automatically Reynolds number low, because NR equal to, there is a dV rho by mu. If viscosity high, then what will happen? Viscosity values are high, then Reynolds number get decrease. For rho Reynolds number system, the increase in viscosity, so generally increase the drag force acting the particle. So automatically if highly viscous liquids fluidize the particle, we need more easily than the low viscosity of fluids. Then what will happen? Porosity. The porosity is another representation of fraction of, we call it as a void volume, pore volume. So, porosity represents the fraction of bed occupied by the fluid here. So, beds with higher porosity, what will happen? Beds with higher porosity provides larger the flow passages, of course then lower hydraulic resistance, then easier the fluid movement. So, since the porosity affects also drag force and pressure drop, it also influences the minimum fluidization velocity. So, that is only we have totally 5 variables we discuss here. So, what will happen? Porosity, then fluid viscosity, fluid density, particle density, particle diameter. These are the parameters we called variable also sometime. So, what is the advantage of and limitation of fluidized bed? So, the advantage of fluidized bed, excellent mixing compared to the packed bed, because the packed bed compared to this one, it gives very good excellent mixing. The temperature is uniform throughout the column, because it is a completely the fluid particle getting suspended and try to maintain the uniform temperature. So, there is a high oxygen transfer, then automatically mass transfer also very high. So, then automatically there is the channeling will get reduced compared to packed bed. Of course, the advantage is a continuous operation, no need to be a batch operation, it is a very useful that one. So, when you use any packed bed or fluidized bed, there is a limitation. So, here also the fluidized bed, what is the limitation here? Particle attrition, then definitely catalyst loss is there. When sometimes you increase the velocity, the catalyst will go outside. So, there is a chances are there. The hydrodynamics, definitely complex hydrodynamics. There is a gas, there is a liquid, then solid, all transferring taking place. Then the hydrodynamics, to understand, it is a very complex here. Of course, we need higher energy consumption compared to packed bed. Then the scale up, you want to scale up, you have to see very carefully to scale up, it is difficult to scale up the process. So, what are the key takeaway here? So, this fluidization, whatever fluidization occurs, there is a drag force equals to particle weight, that is called minimum fluidization velocity. The minimum fluidization velocity definite we discussed. The bed expansion results from increased void fraction. So, the void fraction increases, the bed expansion also increases one. That solid volume remain constant, that is very important. The solid, whatever the solid volume, that is remain constant, the bed, but bed will get expanded constant during the expansion. So, that fluidized bed exhibits excellent heat and mass transfer compared to packed bed. So, it definitely is very useful for biochemical reactor, then some wastewater treatment process, all the fluidized bed is very important. These are key takeaways here. So, then we will discuss today minimum fluidization velocity. What is minimum fluidization velocity? So, there is a liquid or gas is always flows upward through the packed bed of particle, it remains stationary at low velocity. Whenever the low velocity, it remains stationary, because the weight of the particle, what of the particle is greater than the drag force exerted by the fluid. So, the fluid velocity increases, the drag force also increase. Then if the drag force increases, then definitely that we call as a critical velocity, where the drag force, upward drag force, we write Fd, that is equal to W effective. The both are we get equal. So, once the UMF cross that one, minimum fluidization velocity cross that one, then at this condition the particle begin to suspended in the flowing fluid. So, the packed bed now is moving to fluidized bed, slowly transforming taking place because of the minimum fluidization velocity. So, the critical velocity we called as a minimum fluidization velocity. It is one of the most important design parameters in bioprocess engineering, minimum fluidization velocity. So, example, you assume the consider packed bed column filled with the catalyst particle. So, initially the particle touch each other, because there is a void spaces or remain constant when they start that one. So, pressure drop also increases with the flow velocity. When they start that one, definitely the pressure drop also get increases, because it is falling in the packed bed. So, the pressure drop or the pressure difference definitely will get increases. So then once start velocity increases, the velocity get increases, then automatically the drag, although the large drag on the particles. So then automatically at particle velocity, the particle, whatever the particle, just start to lifting the from another particle slowly get this one. So then the fluidization starts. That point we called as a incipient fluidization or minimum fluidization velocity, that we always all are same that one. So after this point, that if you cross the minimum fluidization velocity, then the particle becomes suspended, the bed get expands. So then automatically the pressure drop, the delta P is the constant when it above the UMF, the above the minimum fluidization velocity. So then what is the derivation of the minimum fluidization velocity? The force balance, first we are writing the force balance at the minimum fluidization here. At minimum fluidization there is a upward force that due to pressure drop that must exactly the balancing the effective weight of the particles. So there we always discuss the previous one. So there is a balancing, whenever get increases, the drag force get increases, then automatically the bed get expand, the fluidization also starts. So then the pressure difference across the bed, we always write delta P, there is a delta P. Then the cross sectional area we are writing A. So we know we always write P equal to F by A. It's a very simple formula. So then there is a force, the pressure, okay, the drag force here. So pressure force, we write Fp equal to delta P into A. So then now that determine the effective weight of particles, we have to find there is a total bed volume is there, total bed how much of volume. So there is a V is the total bed volume, LMF minimum the fluidization length, this one, then area is the how much cross sectional area we are using here. So then is a total bed volume. So how much the fraction of the occupied solids here, the only the fraction of occupied solids, we have to write 1 minus of x log mf, that we call it the minimum fluidization velocity and minimum fluidization porosity. Because since we are talking about the minimum fluidization, we are writing mf everywhere. So here also mf, minimum fluidization length. So that's only we are writing LMF, minimum fluidization into area. So then the solid volume we are writing solid volume Vs equal to LMF A. There is no unit for this one, and LMF A area is there. So we called as a solid volume. Then what is the particle mass? Particle mass we will write for M equal to rho P into Vs. So there is a mass, but if you want to write, then the gravity, if you want to write weight, then there is a gravity G you have to include. So this rho P, then if there is all LMF A 1 minus of x log mf, there is a fraction of this one, then into weight we are considering, then a gravitational that also come point. So W equal to, we got the weight equal to, we derived from this, it's all derivation of minimum fluidization velocity here. So the particle now experiences a buoyancy, because there is a buoyancy force are there, because they are immersed in the fluid. So then we have to write the buoyancy force Fb equal to same way, instead of particle we have to write for rho density. There is a rho density here, rho P, density of particles. So here rho G same way LMF A 1 minus F, this one. Then what is the effective weight? Effective weight we have to always, already we discussed, there is a weight minus the buoyancy force, whatever the buoyancy force that one, we have to subtract that one, then we get the effective weight of that one. So the effective weight here rho P minus rho, this is here already there, the rho P, this one, then rho here, basically we are subtracting equation number 1 and 2. Then we get finally this equation that we call as a effective weight. Then at minimum fluidization, what will happen? The minimum fluidization, the pressure force equal to effective particle weight, there is a drag force, so that we called equal to, both are same. Then we can write the pressure force delta P into A, delta P into A. So, this LMF we know A into know, then 1 minus of x long MF, because we got from the previous one LMF after rearranging this one. So, we can write delta PA here. So, there is both side A is there common here, and here also A get cancelled, then we get the pressure drop equal to delta P equal to LMF of 1 minus x long MF, the MF called minimum fluidization here, then the density difference into G. So, then it is divided by LMF, because only if you write delta P, that is a pressure difference, then the pressure gradient delta P by LMF, that is called pressure gradient. If you only write delta P, then is we called as a pressure difference. So, the pressure gradient at the minimum fluidization, we get this equation delta P by LMF equal to 1 minus of this one rho P minus rho into G. So, the above equation state that the pressure drop per unit equal to the effective weight of particle per unit volume of bed, whatever this one. So, it definitely depend on the particle density, then fluid density, then bed voidage and gravity. But it is not giving directly depend on the flow velocity. You just see here, there is no velocity here, it not depend on the flow velocity, because this equation valid only for the onset of fluidization. So, there is no velocity. So, then of course, we have to incorporate with our Ergun equation. So, the previous equation tell us the pressure drop required. However, we still need to determine the velocity that produced from the pressure drop. So, definitely then we have to use the Ergun equation to modify that one. So, this part we know that if for irregular particle, the Ergun equation becomes, we write delta P by L equal to 150 of this one. We already know that the pi s is a sphericity. If sphere, the pi s equal to 1, but irregular particle, it go decrease that one. We already discussed. Then dP is the equivalent particle diameter. So, the delta P by L equal to this equation. So, there is a viscous loss and there is a inertial. So, both them is we are incorporating here. So, that we called as the Ergun equation. We discussed this only applicable for irregular particle, because we have to find the shape factor, sphericity, the diameter of particle. Since we are discussing minimum fluidization velocity, the same equation we have to write epsilon equal to epsilon MF, then V velocity, we can write V of MF minimum fluidization velocity, so that we have to modify the equation. So, that is the way here. Then L also, the length of this one we have to write L equal to LMF. So, there is a substitute all this one, then the pressure drop all, then we can rearrange the equation. This is a final using this equation for fluidization velocity. We can use for the same Ergun equation, the fluidization velocity. So, after rearranging, there is a minimum fluidization velocity VMF, because V stands VMF here, then the porosity converted in terms of x long MF minimum fluidization, L also will go to LMF. So, then the delta P, the equations are there, you rearrange, then finally we get this equation. So, what is the key takeaway from here? There is a minimum fluidization occurs when the drag force equal the effective particle weight. They are called as the minimum fluidization velocity. The pressure drop at the minimum fluidization depends on the bed voidage, then the density difference. The Ergun equation also predict the velocity required to generate the pressure drop. So, then the resulting equation solved determine the minimum fluidization velocity, that is the VMF here. So, finally, the parameter is the fundamental, definitely we need the design of the fluidized-bed reactor. We need minimum VMF, minimum fluidization velocity, any biochemical and pharmaceutical and wastewater treatment process. So, what is the expansion of fluidized bed now? If we get expand, what will happen? The same equation, we got the equation, if it expand, what will happen? So, there is a, when liquid gas flows, then automatically getting expansion, and then the particle to separate one to another that one. So, initially the whatever the particle remain fixed, the pressure drop also increase, because that is a fixed bed or packed bed. So, once the minimum fluidization velocity occurs, then automatically the particle becomes suspended. So, then the velocity also further increase, then it goes wide space also increase, then the particle remains always get fluidized. So, that phenomena called as the expansion of fluidized bed. So why we need to bed to expand? Why does that one? Because the upward drag force become larger than force, definitely it's almost close to the support the particles. So then additional flows also cause the particle to move further, and then porosity also to increase, then bed height also get increase, the particle still remain, get suspended here. So there is increasing fluid velocity, then more liquid to occupy the bed with the larger volume, allow always better mixing, better mass transfer here. So that's only the fluidized bed are widely used in the biotechnology problems. So the flow through the bed remain predominantly, that is the laminar flow. The laminar flow for fluidization here is less than 20, LR equal to less than 20. So diameter of particle, velocity, density, then mu is the viscosity. So there is a two equation, there is a viscous term, then inertial term, two terms are there. So since we are talking the Reynolds number, the low, then automatically the inertial term is neglected, only we have to take a viscous term here. The particle remains uniformly fluidized, there is no channeling and bypassing, it is a steady state operation. So this equation we know, we already got from the previous ergon equation, we know already, because only viscous term we are adding and inertial term we are not adding here. So there is a V dash, the superficial velocity. So at fluidization starts, we can write delta P equal to, we already derived that one, the density of that one. So particle density, fluid density difference, this one. So then the divide by bed height, we can write, that's called pressure gradient. So then this delta P by L and this delta PL, you both equal, then we start to solve the equation. So solve for superficial velocity, so multiply both sides this one. So then we get a V dash equal to, the final equation V dash equal to this one. So here V dash, then we can write this one is in terms of K1 for definition, then finally the V dash equal to K1 of epsilon 3 by, because we can write K1 equal to this one, then epsilon 3 by 1 minus epsilon cube. So that's a for superficial velocity to find the fluidized bed, V dash equal to K1, the K1 is again function of this one, the density of particle, then the difference in density, and then G viscosity all. So we can write V dash equal to K1 epsilon 3 by 1 minus epsilon. So now if we get expand, so the only the bed reaches the minimum fluidization velocity, that is V dash equal to, you keep other as a constant. So then you can always, if you want to any proportional, then you can take a K1 remove, then we can write V dash equal to proportional that one. You want to remove proportionality, then add that one K1, but K1 again the function of this one. So then the void fraction, the porosity of the bed also increases here, and the bed expands vertically, resulting in a greater bed height. The solid particle remain, always get suspended while allowing easier the passage of the fluids. So the bed height expansion again, we know that when Vs equal to AL naught 1 minus epsilon naught, that we already, the solid volume we write like this. If it get expanded, what will happen? If expanded condition also, Vs equal to L naught to L, it will move to L naught to L, the porosity equal to epsilon. Then if you both are equal, then automatically the solid volume remain constant, because the solid volume remain constant. So then Vs equal to after fluidization Vs. So both equal, then we will get the equation for the predict the expanded bed height, because we can get L equal to L naught, the initial one, then porosity 1 minus epsilon. Thank you.